let's look a little bit more at building and balancing reactions first, and then we will look into the actual stoichiometry calculations, okay? So give me, as we start to look towards our next segment, which is stoichiometry, right? That's our big part of our chapter. Remember, do you remember what I said stoichiometry is? What's the big picture for stoichiometry? Do you remember? It's okay if you don't. We talked about it kind of at the beginning of the chapter. Putting quantities to chemical reactions, right? Putting actual numerical values to chemical reactions. So in these stoichiometry problems, you will build them from the ground up. I'll say I have 10 grams of sodium chloride and 15 grams of lithium nitrate, and I want to know how much of my product can I make, right? So you have to build these problems kind of from the ground up. So it's like high stakes, but just like awesome when you get it done. You know, you just feel so good when you get the problem done, okay? So that's really what we're working towards, is being able to put true quantities to chemical reactions, okay? And so to do that, we've looked at all of this prep work. We've learned how to convert from moles to grams to molecules to whatever. We've learned how to balance chemical reactions. We learned how to name molecules and build molecules. And now we're going to kind of put all of that together. Okay, so all of that stuff's going to come together. But I want to talk about, how do we build a chemical reaction? How do we know what the products of our chemical reactions will be? And we're going to focus most of our time on double displacement reactions. Okay, so can someone remind me what a double displacement reaction is? We looked at types of reactions a little bit last week. What happens in a double displacement reaction?
The anions and the cations switch places.
That's right. Cations and anions from each molecule switch places. So they both get new partners. Okay? So it looks like our base formula looks something like this. Some compound AB plus some compound CD. What would it yield? Right? If this is a cation, anion, how would they come together here? A, D, and then plus what else? C, B, right? It has to go cation first, then anion. So remember, the outsides come together to form one, and the insides come together to form one. Okay, so we will start getting reactions where you are only given the reactants. You have to build and balance. Okay, that's our goal, is build and balance our reaction. Okay, so here's how it works. This problem right down here says potassium nitrate combines with manganese 2-phosphate. So we have to build those chemical formulas correctly first. Then we'll predict our products, and then we'll balance the reaction. So it's kind of 3 steps here. Okay, so let's go ahead and go potassium nitrate. Potassium is +1. Nitrate, do we have that memorized still? NO3, what's our charge? -1, good. And so how do those fit together? Just perfectly, right? So my first reactant is KNO3. Okay, so because I'm building my chemical reaction here, my chemical equation. Combines with manganese 2-phosphate. So manganese is Mn, and how do we know its charge? It's from the Roman numeral, right? It's right there. So Mn plus 2. And phosphate, where, if I don't have phosphate memorized, where will I find it? In the box, right? In the box, because it's a polyatomic ion. So tell me, phosphate is PO4 minus 3. So how will those fit together? Do we need to crisscross? We do. Okay, so we need to go MN3, PO4, 2. Okay, are we remembering that whole segment from our naming molecules chapter? I hope so, right? That should be something that we feel comfortable with, because we don't have time to have to really think really hard about that, right? We want that to be pretty natural, okay? So there's our reactants. Now we have to predict our products, okay? We have to build a double displacement reaction. And so based on the fact that it's double displacement, I know what are going to come together here. My outsides and my insides, okay? But will I automatically go KPO4 2? I don't do that because this is not balanced, right? KPO4 2 is not a correct ionic formula. So I have to start over knowing that, okay, potassium is a +1, phosphate is a -3. And so my formula really will be K3PO4. So just because it has a subscript here does not mean that will carry over to the product side. I will worry about balancing the reaction at the end, right? For right now, I'm just building the formulas correctly. So just because there's 2 phosphates here, I don't need to worry about there being 2 phosphates yet. I'll balance that at the end. My formulas have to be built correctly. Okay, my other product will be manganese and nitrate, okay? And so we know manganese was a +2. We're going to keep that. Mn is +2. Nitrate is NO3 -1. And so how will that come together? Mn parentheses NO3 2, right? Because my 2 is going to come down. My 1 is going to come down. And so there is my reaction. Currently, it is built and not balanced yet, right? It's just built. You're going to hear me say build and balance a lot. And that's what I mean. This is build. Now we have to go back and balance, okay? Do we feel comfortable moving forward without the list? Or do you still kind of like the list format for right now? Yes, no? I'm getting mixed yes and no, okay? I think the more you do it, the less dependent you'll be on the list. But we can still go ahead and write it out for this one. Okay, so if I'm going to balance my reaction, I've got potassium, I've got nitrate, I've got manganese, and I've got phosphate. I'm going to keep those polyatomic ions together because they stay together on both sides. So I have 1. How many manganese do I have? 3. And phosphates I have 2. Potassiums I have 3, 2, 1, and 1. Do we agree on our count? So now I'm just looking for an easy change to make to jumpstart my process. All of these changes I would consider easy because I'm going from one to something else. So I'm just going to pick one. I'll start with potassium. I want to have 3 potassiums on the left, so I need to go ahead and put a 3 there. That changes potassium to 3, nitrates to 3. I can already see I'm going to run into a problem with the 3 and the 2, but I'm just going to figure it out later. Okay, do you see why I'm going to run into a problem? I'm going to have to eventually get that up, but I'm not going to worry about it for right now. If I want to, I could double it, but I'm just going to wait. Let's say that now my next easiest change is probably manganese. So I'm going to come put a 3 there, and so that makes it 3 and 6. And so now I'm able to jump over and fix nitrate again. So instead of being a 3 there, I probably am going to want that to be a 6. Okay, so now I've changed my potassiums to 6, nitrates to 6. Now it's going to bounce me over to change potassium. What coefficient will I need right here? 2. So that becomes a 6, and it makes my phosphates 2. And so now it looks like we're balanced. Okay. So I saw a problem early, but I didn't let that rattle me, right? I moved into another easy change, and then I was able to start bouncing back and forth, which that's really the goal. You want one change to lead you into your next one. Okay, if it doesn't, then just take a look at your list and find out what's my next easiest change, and then go from there. Okay, does that feel comfortable? So we build and balanced, right? That was our goal, built and balanced. Any questions about building those compounds or making them balanced? Okay. Let's do this top one together, and then we'll try the bottom one on our own here, okay? Nickel 3 carbonate combines with silver sulfide. Okay, and we're going to do this one together again. Nickel 3 carbonate. Nickel is Ni. And it's got a +3 charge. Where would I find carbonate if I don't have that memorized? In the box, okay? But wouldn't it be easier if we had them memorized? Maybe that's why I had you do that, right? See how much easier it is if I had it memorized? Because I know it's CO3 - 2, right? So we're going to make sure that when we cross those down, we're going to need a crisscross here. Would you agree? Okay, so we're going to crisscross that, and it becomes Ni what? Ni2 parenthesis CO3 parenthesis what? 3. Good. And can I reduce those 3's? No, I cannot. Okay, that's one of my reactants. My next reactant is silver sulfide. So silver, do you know what silver's chemical symbol is? Ag. It's number 47. It has a +1 charge. And sulfide, remember, is just sulfur by itself with the charge. It's not in the box. So sulfide is S -2. And so it becomes what? Ag2S. Very good. Okay. Now for our products, we will have nickel combined with sulfide and silver combined with carbonate. Okay. And it might be helpful for you to draw those arrows to really give yourself some direction here. But if silver is going to combine with nickel, Ag is +1 and, oh, no, I said that backwards. So sorry. If sulfide is going to combine with nickel, I'm going to just keep that one first. Nickel is +2 and sulfide is -2. So how do those fit together? Perfectly. So here's a problem. Here's a problem we might run into. If you did the crisscross and you left it as Ni2S2 without reducing it, you would not be able to balance the reaction. You would run into problems balancing. So we need to make sure that those two, we do reduce those down, and so it just becomes NiS. That's going to be really important for the balancing. Did I mess something up?
Is it Ni3? Yeah, it's
Oh, yes, I did. Sorry. Yes. Okay, so yes, yell at me next time before I'm blabbing on about something wrong. Okay. Ni, how about this? +3. Thank you, from our 3 right there. Okay, so now it becomes what? Ni2S. Thank you. Okay, good. Okay, very good. And our last one is silver carbonate. So silver is +1 and carbonate is -2. So our final formula would be Ag2CO3. And do I need to bother put CO3 in parentheses, or do I need to bother putting the 1? Nope. Okay, very good. So we're built, but are we balanced yet? We are not. So let's go ahead and balance. I'm going to try to do without the list, okay? If I'm going to go without the list, I'm just picking a starting point here. I don't know. I see that I have 3 carbonates here, but I only have 1 on the right. So that's going to be my starting point. I'm just going to go 3. So now I know that I've changed my silvers to be how many? 6. So I'm going to bounce that over. And I need 6 silvers, which means I should put a 3. That changed my sulfur to 3. So I'm going to bounce over and look at my sulfur. I'm good. And so what's the only element I haven't examined yet? Nickel. And I'm at 2 and 2. So I think it's balanced. I think that's it. Right? Do you see how we can work without the list? Pick a starting point and then let it bounce you to your next option. Okay? I just want to show you that in case that's helpful. But you are always welcome to make the list. I just don't know that we have time for that every time in class. Okay? So we're going to start kind of being able to move a little bit quicker through those balancing reactions. But does that seem comfortable for everybody? Good? Okay, why don't you try the last one on your own? I'll give you a couple minute head start and then I'll get it up on the board. We're going to start with a concept called mole ratio. And we talked about mole ratio just a bit when we examined individual atoms versus total compound, didn't we? When we started comparing the atoms of just potassium in the compound, we looked at something called the mole ratio. And that shows us the ratio of an individual to the whole. But now we're going to look at the mole ratio in terms of how 2 compounds compare to one another, okay? So a mole ratio says it's a conversion factor that relates the amounts of moles of any 2 substances in a reaction. So it could have been the part versus the whole, like we already examined, or it can be the the ratio between 2 separate compounds. So if I asked you what's the mole ratio between potassium chlorate and potassium chloride, what would you tell me? What's the ratio for those 2 compounds? First of all, you got to know what potassium chlorate is and potassium chloride. In this reaction, which one What's the ratio? 2 to 2, right? We're just looking at the coefficient that goes in front. Because if I speak this reaction in words, this says 2 moles of potassium chlorate breaks down to form 2 moles of potassium chloride and 3 moles of oxygen gas. That's what's happening in the reaction. You can also speak about this reaction on a molecular level. So I could say 2 molecules of potassium chlorate break down to form 2 molecules of potassium chloride and 3 molecules of O2. We just don't look at it on such a small level. We use them in moles. Okay, yeah, go ahead, Maddie. This is one of the products of the reaction. So these atoms split apart. We've got a total of 6 oxygen atoms here. And those, as in terms of the reaction, whether it was heat, I don't know what happened in the reaction, but something caused them to break apart. And so potassium chloride stayed together and oxygen gas was one of our other products. Okay, what type of a chemical reaction is this? We're taking something big and we're breaking it down. Decomposition, good, decomposition. Okay, so if I asked you for the mole ratio between potassium chloride and oxygen gas, what would you tell me? 2 to 3, good. And so we're going to put that ratio into our T-chart. We're going to be able to use that ratio in our T-chart. The mole ratio is the only time, or the mole ratio always has to be happening in moles, right? We can't compare grams of one to moles of another. Remember we kind of talked about that? Grams of two different molecules don't give us an idea of the quantity. They just give us an idea of mass. Remember how we gave the example that 1 gram of hydrogen and 1 gram of oxygen have the same mass, but they're nowhere near the same quantity of atoms. Remember how we kind of talked about that example? 1 gram of hydrogen is a whole mole, but 1 gram of oxygen is only like a 16th of a mole. So it represents a much smaller quantity of atoms. So we always have to compare moles of our substances. So that's what we're going to make sure that we do. Another thing I want to talk about with this stoichiometry calculations is that when we do problems, we are allowed to compare any 2 substances in our reaction. We could even say, let's just pose some hypothetical questions here. We could say, if I produce 16 grams of oxygen, how many grams of KCl could also be produced, right? I can answer those 2 questions really without knowing anything about my starting amount. I can compare or answer questions about any 2 substances in my reaction. It doesn't just have to be that I'm given a certain amount of my reactant and I want to find out how much product I can do. I can compare any 2 things. Okay, so we'll look at that as we walk through our problems, okay? So let's go ahead and start here. We're going to start with mole to mole conversion. So these are the easiest types because we're going to start with moles. We'll look at our mole ratio, and that's really all we have to do, okay? So this says, here's our reaction up top. I think the reaction is already balanced. I see a coefficient here, so I think it's already balanced. So we're gonna trust that it is balanced. You might want to check that when you get to actual problems, though. This says, how many moles of lithium hydroxide are required to react with 5 moles of CO2? Okay, how many moles of lithium hydroxide are required to react with 5 moles of CO2? So here's what I like to do. I like to kind of write my values above or below the reaction so I can kind of focus in on what I'm examining, right? I want to know, and my question mark is the number of moles of lithium hydroxide, and I'm starting with 5 moles, okay? So the question we want to ask is if we combine these 2 and we want to make sure we use up all 5 moles of CO2 in our reaction with nothing left over, right? We want to use up all of it. How much lithium hydroxide would we need to add to our reaction? Does that kind of make sense what we're looking at here? If I start with 5 moles of carbon dioxide, how many moles of lithium hydroxide would I need? Okay, that's the question. So we always start our T-chart with what we know. 5 moles of CO2. Okay, and just like any T-chart, what has to go diagonal? Moles of what? Moles of CO2. Does it do me any good here to go to grams of CO2? or molecules of CO2? It does not, because I want to shift my focus from CO2 to moles of lithium hydroxide. And so here is the step that I can do that, because this right here is my mole ratio step. I'm able to switch examining CO2 to lithium hydroxide, right? I can switch in that spot in the mole ratio step. Okay, the mole ratio step is the only place that the mole doesn't necessarily get the 1. And these values come directly from our balanced reaction. So I need to go and look at my problem and say, what coefficient does moles of CO2 have? Or what coefficient does CO2 have in my reaction? It has a 1, so that's coincidental. But lithium hydroxide has a 2. Okay, and so I've put in now the ratio that we need to keep intact. And so if I've canceled moles of CO2, I'm in moles of lithium hydroxide, which is what I wanted. Now I'm done. I just do the math. That means I need 10 moles of LiOH. Yeah.
So are we only using...
Let's balance this one first. Is it balanced on your handout or no? No. Okay, so let's go ahead and balance first. Go ahead and get it balanced, and I'll do the same. Okay, relatively simple balance there. Did you have 2, 2, 1? Okay. This asks us how many moles of O2 will result from the decomposition of 0.66 moles of hydrogen peroxide. Okay, so again, I like to zone in, kind of focus in on what I'm looking for. This asks me how many moles of O2 will result from the decomposition of 0.66 moles. Do you know which one hydrogen peroxide is? Can you figure it out by process of elimination? Right? I know hydrogen peroxide is not this, and I know it's not this, so it's got to be this one. Right? Sometimes that's all you have to do. Right? That hydrogen peroxide is not named how we would typically name it, but you can figure that out, right? Okay, so we want to know how many moles of O2. So I'm going to start my T-chart with what I know. 0.66 moles of H2O2, and I'm going to encourage you to keep the chemical formula in your T-chart. While we go through this, we're going to see a swap. So we need to make sure we're really clear about what we're canceling and what we're not. Okay, so now I'm going to bring moles of H2O2 to the bottom. And what am I going to go to? Moles of O2. Okay, and so I'm going to go check my T-chart now, because what's this step called? Mole ratio step. Okay, and it's the only one where moles is not guaranteed to get the 1. We're going to go find those values, from our balanced reaction. So H2O2 will get a what? A 2. And oxygen gas will get a 1, right? Because we assume there's a 1 right there if I don't list anything. We assume there's a 1. And so now I've canceled moles of hydrogen peroxide. I'm left with moles of oxygen, which is what I want. So now I do the math. I multiply across the whole top, divide by the whole bottom, and I get 0.33 moles of O2. Okay, do we see the relationship here? Right now it says I'm going to produce half of what I started with, right? And so in terms of moles, that should make sense to us. 0.33 moles of O2. What's our conversion factor if we're going to have to go to grams or get out of grams? What do we use to help convert that? Molar mass. Good. Not Avogadro's number for grams. Grams is molar mass. Okay, so this says, what mass in grams of glucose is produced when 6.4 moles of water reacts with carbon dioxide? So we need to balance this reaction first. Okay, so let's go ahead and balance this one. Oh, no. That's not what I want. This balancing was a little tricky because I have oxygen here in 2 places. We had to account for that before we could put in that last coefficient. But is that similar to what you had it balanced as? 6, 6, 1, 6. Okay. All right, let's go ahead and look at our question here then. It says, what mass in grams of glucose? So my goal is to find grams of glucose. Did I know this was glucose? Not necessarily, but I knew it wasn't any of the other ones, right? So I can by order or by, process of elimination, I can figure out that it's got to be that one. So I'm looking for grams of glucose, and I'm looking for when I have 6.4 moles of water reacting with carbon dioxide. Does that change my problem at all? It's just telling me what it's reacting with. It's not making any difference. So I'm starting with 6.4 moles, and I want to find out how many grams of my product can I make. Okay, what this is telling me is that the amount of CO2 that's present is not affecting my reaction. So we just know that we at least have enough CO2 to react all 6.4 moles of that. Does that kind of make sense? CO2 is not changing our reaction right now, so they don't mention it in the problem. We will eventually look at problems and where you have to pay attention to both, but for right now, we're just under the assumption that we're starting with 6.4 moles of water. We're going to use all of that up in the reaction, and we'll have leftover CO2, right? We have enough of that, so it's not part of the problem. Does that kind of make sense? Okay, so let's start with what we know. 6.4 moles of water. Do I need to bother putting in like the liquid gas? No, I don't, right? That's not changing my calculations at all. So my goal is to go from moles of water to grams of glucose. Are we understanding that process? What has to go here? Moles of water. And what has to go here? Not carbon dioxide, because that's not part of my reaction. That's not part of my problem. I'm only focused in on these two, right? Moles of what?
Glucose.
Good, moles of glucose. I'm going to switch my focus. I'm going to switch my focus from water to glucose because I want to find out grams of glucose. So I cannot go directly, let's go back for just a second. Would it do me any good to go grams of water here? Nope, that doesn't do me any good. I also cannot go grams of glucose right away because I can't switch unless they're both in moles, right? I can't gloss over the mole ratio step. So this has to be moles of C6H12O6. But my problem's not done here. I'm going to bring this down to cancel it and end up in grams of C6H12O6. So that's going to be molar mass. Yep, let's go ahead and start putting in our numbers here. What's the numbers that will go in for this mole ratio step? 6 will go with water. Good. And what will glucose get? A 1. Good. And so now when I keep moving, now we're to a mole to gram conversion, which means moles always gets the 1. And I find molar mass of glucose to put in there, right? Because I'm saying, what is the mass of 1 mole of glucose? So did we get 180? 180 grams? Okay, so once I'm here, I'm going to check. Moles of H2O is canceled. Moles of glucose is canceled. Grams of glucose is what I want to end up in. And so now I do my math. I multiply across the whole top, divide by the whole bottom, and I get a value of 192 grams of glucose. Expected range. So I started with a little more than what I needed, right? And I was supposed to end up with around 1 mole and a little over 1 mole. And so I ended up with a little over 1 mole, right? So it fits within our range here. Very good. Okay, let's try this one here. Actually, I'm going to change this question. I'm going to change the question. Sorry. I'm going to go backwards here. I'm going to change this to how many moles of O2 are required to produce 3.12 grams. I want us to start in grams this time and end up in moles so we can see both sides of the conversion, okay? So this says how many moles of O2, and I've already got it balanced for you this time, are required to produce 3.12 grams of H2O, right? Do you see how I write those by my reaction? So I'm really focused in on that ratio. I'm not getting distracted by the other things in the problem. I'm just looking at those two compounds, okay? Do we understand the question it's asking? I need to produce 3.12 grams of water for some reason, so I want to figure out how many moles of oxygen have to go in order to do that, okay? Let's start with what we know, 3.12 grams of water. It makes no difference that we are starting with a product. It doesn't matter. It works the same way. So we're going to go 3.12 grams of water. And so what has to go diagonal first? Grams of water. And what should I probably go to? What does my middleman have to be? Moles. Can I go directly to moles of O2 here? I cannot. I have to stay moles of water. Let's keep going with the units first before we put numbers in. But I don't want to end up in moles of water. I want to get rid of moles of water. And I want to go to what next? Moles of O2. Okay? And do I need to continue on? Or I'm going to stop right there because I want to have moles of O2. Okay, so now let's put in our numbers. In this step, we're just doing gram to mole conversions, which means mole gets the 1, and the molar mass of water is 18. This now would be our mole ratio step. Okay, and so our ratio here is 5 to 6. Do you see how neither one of those got the 1? Right? In the mole ratio step, it's not guaranteed that anything gets a 1. So now I've canceled grams of H2O, moles of H2O, and moles of O2 is what I'm left with. So I'm going to do my math. 3.12 times 5 divided by 18 divided by 6, and I get 0.144 moles of O2. So that's how much I need. Do you feel like that fits kind of within an expected range? Did we need to produce very much product? We only wanted 3 grams of product. So I think it makes sense that our mole value here is pretty small of what we needed to put in. Okay, how are we feeling about that? Do you notice that the mole ratio didn't come second there? Right? We had to work our way to that. Are we feeling comfortable with how the process works? Good? Like them? Okay. So the conversion itself is something we're really good at. Now we're just adding the ratio part, and that's where we make the switch, okay? Okay, let's expand it out again. Now we're going to go gram to gram conversions, and this is as long as it gets, I promise. It doesn't go past 4. So gram to gram conversions. Now we're going to start in grams of our substance and end up in grams of our other substance. So we have to go all the way, okay? But this is as big as it gets, I promise, okay? This says how many grams of water is produced. So how many grams of water is produced if 56 grams of O2 is combined with excess ammonia? Do you think that affects our problem, saying excess ammonia? No, it just means like we're going to have leftover. There's plenty of it there. It's not going to affect our problem. Okay?
They love trying to confuse me.
Eventually it will make a difference, but now it doesn't, so it's good. All right, we are going to start with what we know. 56 grams of O2. Okay, so let's figure out our process here. Okay, it might even be helpful for you to do this. I'm going to go from grams of O2 to moles of O2 to moles of water to grams of water, right? You can make yourself this little path. That's not very clear, sorry. You can kind of make yourself a little pathway if that makes you feel better, okay? But your units will lead you in your T-chart too. So I'm going to go from grams of O2 to what? Moles of O2. Moles of O2 to, can I go directly grams of H2O right here? No, I cannot. I cannot switch compounds if they're not both moles. So this has to be moles of water. Then we're going to get rid of moles of H2O and go to grams of H2O. You see how our units just lead us on to the next until we get to what we want? Now we put in our numbers. Here's my question. If I know the molar mass of O2 is 32, do I put a 5 right here?
No.
I don't, right? When we're doing a mole to gram conversion, moles gets the 1. I need to put my 5 in the mole ratio step. So 5 and 6. And then the same thing is true. I would not put a 6 here for water, right? I'm here back to just 1 mole is 18 grams. I don't want to account for the mole ratio more than once, right? I'm only doing that one time. So 56 times 6 times 18 divided by 32 divided by 5 gives me 19.51 grams of water. 37.8, is that better?
Yeah.
Thank you. Okay, good. Yeah, just yell at me if I do it wrong. It happens. 37.8 grams of water. Okay. Yeah, go ahead, Anna.
So for the last 18 over 1 mole, why I don't understand why that wouldn't be 32. Why it wouldn't be 32?
For which, right here?
Yeah.
Well, the molar mass of H2O is not 32.
Oh.
Right? If it was O2, there it would be 32, but it's water. So we're going to go for its molar mass. Okay. I don't move into, I don't know, do we feel comfortable? Are we ready to try some by ourselves? You ready to try these 3? I'm going to skip over this next gram. You're going to try this one. This has 3 problems. Listen, so you need to balance first. And there's 3 problems for you to try, one of each type. Mole to mole, mole to gram, and gram to gram. They are all using the same reaction, but they're independent of one another. So it's not like your answer from one has to affect the other ones. Does that make sense? Okay, so balance it first. I'll get it balanced up here in a minute so you can check before you get too far into your problems. But I want you to try all 3 of those, okay? The last problem says if this many molecules of tin react with hydrofluoric acid, how many hydrogen molecules are formed? What would I use for molecules? Avogadro's number. And so that makes our problem way easier because I don't have to calculate molar mass. And in this case, molecules would be both, Avogadro's number would be both on the bottom and the top in my T-chart, which means they would cancel each other out and I wouldn't even have to plug it in my calculator. Okay? But the point of this problem is I can mix and match anything I need to in my T-chart. I can start with grams and end up in molecules of another, right? I would just use molar mass first, Avogadro's number second, whatever I need to do. But I can mix and match those different things. Does that kind of make sense? So it's just like we know how to convert with Avogadro's number. So I'm not going to go through it because I want you to have some time to work on the homework assignment. So these didn't copy very well. So I need you to come grab one, but I only want you to do the odd problems. So that's just numbers 1, 3, and 5. Okay? So you only got 3 problems you need to do. You can come grab them out of this stack right here. These ones are the backs. I don't know what happened. So this pile right here, just number 1, 3, and 5.